Today we're going to start looking at properties of linear functions. Linear functions is such an important idea that our whole next unit is devoted to linear functions in particular. So a linear function is a relation, and what you have is a constant change in the independent variable results in a constant change in the dependent variable. And if things are constantly changing at the same rates, if you plot all those points and join them, they make a straight line. That's why it's called a linear function, because it makes a straight line. We call this ratio, if we look at how much the x has changed and how much the y has changed, we call that the slope of the line. We have a French theme today. We use the letter M to represent slope. And M comes from the French word for mountain. Not the English word for mountain, the French word for mountain. And I think there's some truth to that, because it was a French mathematician that did a lot of the study of equations of lines. So our formula for the slope is look at how much the y variable changes and look at how much the x variable changes. In English, we simplify that to rise over run. Rise is how much something changes up and down. Run is how something changes horizontally. Anytime you have a line, was everybody able to get everything there? Do I need to go back? Rise over run? It's good. Anytime you have a line, you can write it this way with the slope and the y-intercept. Do you remember when we tied knots in the string at the beginning of this unit and we looked at everybody's graph? Where the graph started was how long your string was to begin with. And that was on the y-axis. We call that our y-intercept, or the initial place where you start from. Then, every time we tied a knot, the string got shorter. Theoretically, if you are a very consistent knot tire, you always make your knots exactly the same and exactly the same tightness, then every time you make a knot, the string should get shorter exactly the same amount. Well, that change represented the slope, right? For a lot of you, your slope ended up being -2 or something, that it went down 2 centimeters each time we tied a knot. Your x still represents your independent variable, and your y represents your dependent variable. So what did we have control of in our string and our knots? How many knots we made was our independent variable. What depended on making the knots was the length of the string. And we do a whole unit on y equals mx plus b next. But right now, we're just starting to get introduced to it. So here we have a picture of car rental cost. We have a dependent variable, cost, and it's going to cost you more money if you drive it for longer. Okay? So let's look a little bit. What does this mean? How much is it changing? Well, if we look at the green lines here, The green lines represent the change in the horizontal. In our formula, we call that the run. The blue lines, they represent your vertical change. On our formula, we would call that our rise. So if you were to pick one section of this, it looks like you're going up 20 and you're going to the right 100. So our slope, our change in the dependent variable is $20. Our change in the independent variable is 100. If we simplify that, it's costing you 20 cents a kilometer. So we can write a sentence for this. The rate of change, or the slope, is 20 cents a kilometer. That means for each additional kilometer you drive, you have to pay 20 cents more. Let's look at this equation a little bit more. What does the Y-intercept mean? You haven't went anywhere. How much is it going to cost you if you don't go anywhere? Yeah, $60. That's not a very good car rental choice to do, but you can do that. You're like, I'm going to save money on kilometers this time, so I'm just going to rent it and park it there. Nice. Now, it doesn't say how long you could rent this for. So maybe if you needed somewhere to store something, you could rent for $60 is probably cheaper than renting a storage compartment and just open the trunk and store stuff in there for a year. I don't know if they'd let you rent it for a year. But according to this equation, it would cost you $60 to rent it. And it doesn't say if that's per day, but often a company will have you pay an initial amount, and then here in this case, each kilometer more you drive costs you an extra 20 cents. So we could write an equation for this. Remember, the equation of a line is always the slope plus the y-intercept. In this case, our slope is 20 cents, and our y-intercept is 60. And you could either write this is in y equals mx plus b. We could also write this as a function. So in function notation, I might use c because c stands for cost. C of x is 0.2x plus 60. And you could use your function notation to solve all sorts of different questions. Like, for example, how much is it going to cost you to drive 200 kilometers? So we could find that out by looking at our graph. Can you see on your graph that you have a point? 200 kilometers right here. This point is 200, 100. So according to our graph, if you drive 200 kilometers, it should cost you $100. Let's see if our equation says the same thing. So our question is, what is the cost if you drive 200 kilometers? Well, from our graph, we already know the answer is $100. But if we wanted to use our equation, we're trying to find the cost when x is 200. So you would plug in 200 for x. You go to your calculator, what is 0.2 times 200? It's 40. And then 40 plus 60.
Oh, good morning.
Good morning.
Sorry for interrupting.
So we already wrote this down. I know it's on your next space, but you can highlight everything so far in what it stands for. And we used X, but you could use a different letter, in this case D, for distance. Now, if you have a table of values, and the question asks, does this make a straight line or not? One way that you could do it is to graph it. If you want to create a graph with your independent variable being time, t, and the number of bacteria, n, you could graph it, and then you could say, does this make a straight line or not? Okay? One of the things about drawing graphs is they're somewhat time-consuming. And if they're time-consuming, most students put that into the annoying category rather than the, oh, I can't wait to draw another graph category. Most people don't even have that category. So if we go back to our initial definitions of what does it mean to be a linear function. So this was before, what does it mean to be a linear function? A linear function says that a constant change in the independent variable should result in a constant change in the dependent variable. So let's look at our chart. Let's look at our independent variable. What's happening from 0 to 20? Plus 20. And 0 to 40? Plus 20. And 40 to 60? Plus 20. And 60 to 80? Plus 20. And 80 to 100? Plus 20 again. So in our independent variable, we are having a constant change. We are going up 20 each time. Let's look at our dependent variable. How much am I changing here? Plus 1, and now I'm going plus 2, and now I'm going plus 4, and now I'm going plus 8, and then plus 16. Whew. The amount I'm adding each time is not constant. Okay? Even though you're right, the pattern is that we're multiplying by 2. But multiplying by 2, even though you're doing the same thing each time, isn't a constant increase. A constant increase means that you're adding the same amount each time. So if we graph this one, we would find the following shape. Is that a straight line? No. Okay, good. I'm glad no one said yes if you bend it. No, it is not a linear function. The amount of tax charged based on the amount that you buy. So here, my independent variable has a pattern plus 60, plus 60, plus 60, plus 60. And my dependent variable is going up $3 every single time. GST is 5%. 5% of 60 would be $3. And it looks like every time you pay another $60, do you have to pay another $3 in tax? Yes. And so since we have a constant change in our x values and a constant change in our y values, this is a linear function. If you did graph it, it would make a straight line. One of the things that we do in the next unit a lot of, yes?
It wasn't a linear function
Because in the green, the dependent variable, n, is not increasing by the same amount each time.
Oh, okay.
So you need a constant or the same increase in both your independent and your dependent variables. So one of the things that we practice a lot is graphing lines. What would a relationship between x and y look like if x was always -2? Can you tell me a point on the graph where you have x being -2? So what would the coordinate of that point be? -2, 0 is one point where the x value is -2.
No, it's to the left.
Yeah, you're right. Thank you. Yes. It will be just a vertical line. But can you tell me another point where the x value is -2? -210. Great. Off the charts. Good. What's another point that happens to be actually on the graph? -2, -2. That would be right there. Can someone tell me a creative point? I don't know. These ones are kind of boring. Ooh. -2, 5.6. Oh, that's pretty creative. You got more creative than that? -2 pi. What's 3.14? You want to go about there? -2 comma pi. Okay? Now what we're going to do for the next 45 minutes is try and list them all. No, I'm kidding. How many will there be? Infinite. And if we kept drawing them, can you see you would, they would all be on that line? And so we graph the equation of x equals 2 by drawing a straight line, or attempt to draw it straight. And we can label it x equals -2. Vertical lines will always be x equals something. Is that a function?
No.
No. Vertical lines are not functions.
To indicate that a line continues forever, do you have to put the
Yes.
edge of the screen or the graph?
Wherever you put it. Okay? That would be fine. Generally, we do sort of make our graphs go to the edge of the graph paper that we have. I mean, but technically you could have done it and showed the same thing, making a little tiny thing with arrowheads. It would mean the same thing, but it wouldn't really demonstrate it as well. Okay, so that is a specialty graph where the x value is always -2. I'm going to do it in a different color. What would the specialty graph look like where y was always equal to 1? Horizontal line. You could draw that one, that one, that one, that one, that one, that one. Get creative. That would be the line y equals 1. Y equals x plus 5. Okay. Who gave the last creative answer? Was Thrindu. Thrindu, you get to pick a volunteer. The person that you pick has to tell me one point on this relation. An x coordinate and a y coordinate that makes that equation true. Yeah, just wait a couple seconds, make sure everybody gets nice and nervous and sweaty, and then you can ask someone to tell me a point on this graph. We want to get, try and get all of the nerves as great as possible. Your stomach should start to, no, I'm kidding. Okay. 0 and 5. Is that true? When x is 0, in this equation, is y equal to 5? Does that make that equation true? Yes. Perfect. Oh, need to close that. There we go. 0 and 5 is 1 point. Excellent. Now Bridget gets to pick a volunteer to tell us another point. Nick. What is another point that is true for that equation?
Now, I'm not a smart guy, so I'm not going to get this right now. But I bet my way through on 1 and 6.
1 and 6. Is that true? When x is 1, is y 6?
Perhaps.
If we look at the equation, if I put 1 in for x, does it equal 6? Yes, it does. All right, Nick, pick someone for the next one.
Hey, Regan, how do you do all math? Good. Can I go?
Yeah.
2
2
and 7.
and 7. Ooh, that's looking like that might be the last one on the grid that we can do in that direction. Is this going to make a straight line? Maybe. Regan, pick someone else. Andre.
-5 and 0.
-5 and 0. Does that work? If we plug in -5 for x, do we get 0? Yes, we do. Another one.
Oh, yeah.
Yeah.
Emma.
Nice clarity. Okay. -2 and 3. Perfect. And again, we could spend the next 45 minutes doing more and more and more points. How many points do you feel you need to do before you get an idea of the pattern?
3.
Okay. So in this situation, are you okay if we do that? Nobody picked any decimals, but we could do decimals as well. Someone could plug in -3.24 and find out what it would be.
What would 1 and 6 fall into that line?
Why would 1 and 6 fall into that?
On the side of the line.
It's right here, 1 and 6.
Oh,
You just wanted the point that you had highlighted more than everybody else's. Obviously, 1 and 6 is the best point on that line, just to clarify. So it makes a straight line. How might we have known that this makes a straight line before we graphed it? Well, we wrote out that every straight line has the form y equals mx plus b. In our equation, we have a y, we have an x, we have a plus 5. We have no m.
Oh, is it 1?
It's 1. And so this is our y-intercept. Did that show up on our graph? Yes. 0 and 5 shows up on our graph. And the m, which stands for rise over run, is 1. Can you write 1 as a fraction for me? 1 over 1. Fancy. Okay? What does that mean? That means if you start anywhere on the line, let's go to purple. If I start here, if I have a rise of 1 and a run of 1, do I get back to my line? Yes. A rise of 1, run of 1, back to my line. Yes. Can you tell me a fraction that's equal to 1 over 1? 2 over 2. Is it true that if I go up 2 and over 2, I get back to my line? Yes. Whoa. What if we did 500 over 500? Would we get back to the line? Yes. Eventually. I'd have to jump really high to do 500 over 500. I'm imagining I can jump that high, but I'm not going to try. Okay, I want to try, but no. So if we have an equation that we can recognize can be written in the form y equals mx plus b, that becomes another way that we could graph it. Oh, we did one that was straight across already. Let's do another one. Y equals 5. We'd have this point, this point, this point, this point, this point, this point, this one, this one. Y equals 5. What happens when an equation isn't in y equals mx plus b form? Y equals x squared plus 5. This doesn't have y equals mx plus b. Andre was the last one to tell us a point? No, Emma was the last one. Emma, pick a volunteer to tell us a point on this line. But let them sweat for a little bit and wait. All right. 5 and 1. So when x is 1, will y be 5? You're close. When x is 1, y will be 1 and 6. Pick someone for the next point. Oh. So yeah, 2 and 9 works. Way up there will be 2 and 9. Because when x is 2, 2 squared is 4. 4 plus 5 will be 9. But that's off the screen. That's okay. We'll allow one number to be off the screen. Another one. Pick someone. Aubrey. Can you pick one that's on the screen? We have 1 and 6, which was on the screen. 2 and 9 went off of the screen. What would be a number that would be back on the screen? Now, when finding points, what we're doing is we're picking, you can pick any value of x that you like and plug it in to see what happens. So when we found 1 comma 6, we plugged in 1 for x, simplified it, and found out that it was 6. When we wanted to find 2 comma 9, we plugged in 2 for x, simplified it, and found 2 comma 9. Negative 1. What happens when you square the negative 1, though? What's negative 1 times negative 1? Positive 1, right? Plus 5 will be negative 1 comma 6. Perfect. Pick someone for the next point. I want it to be on the graph. Negative 2 and 9 is true. 0 and 5. There we go. This graph ends up looking like this. But what we were demonstrating is when you go to graph something, you can make something called a table of values. A table of values, what we did is first someone plugged in 1 for x, then figured out when I put that in, 1 squared plus 5, we get 6. Next, someone chose 2 for x, and then we got 2 comma 9. We wanted to keep it on the graph, so someone picked negative 1. Negative 1 squared is still positive 1, plus 5 is 6. Then we tried to go off the graph again, which wasn't allowed, but we talked about the point negative 2 and 9. And then the last one that is nice, that is on the graph, was 0 and 5. There's some not nice points that would be on the graph, right? You could if you wanted to, plug in 0.5 and get 5.25, but then you'd probably need your calculator. Yes?
Isn't that like a quadratic?
It is a quadratic.
Yeah?
Yes.
Yeah.
Very nice.
I knew it was coming. Hold on.
It is a quadratic equation or quadratic function, and the graph has a special name. It's called a parabola. All right, example number 4. Which of the following relations would be linear? Justify your answer. Give the equation for each relation. Hint, make a table of values to see if the relation is linear. A dog sled team moves at an average speed of 10 kilometers an hour along a frozen river. The distance is related to the time. So first of all, in order to make a table of values, we have to think about the situation and say, what's our independent variable? What's our dependent variable? Our independent variable would be time, and what depends on the time is how far. We have to choose units. We have a speed of 10 kilometers per hour, so I'm going to do time in hours and distance in kilometers. All right? What would one point be on this graph? Claire? If you went 1 hour and you're going 10 kilometers per hour, you would have gone 10 kilometers. Whoa. Can we do another point? 2 and 20. Someone said 3 and 30. 4 and
50.
Is this linear? Yes. We know it's linear because Over here, we're going up by the same amount, and here, we're going up. The change is the same. If I went backwards here to 0, you'd go 0. What would this equation be? This plus 10 is how much I'm changing in my y. That would be my rise. This plus 1, that's my change in my horizontal or in my independent. That would be my run. My slope, since this is a line, it has to go y equals mx plus b. My slope is rise over run. My b is my y-intercept or my initial amount. When time is 0, my initial amount is 0. So you wouldn't have to write plus 0, but you can just to help it stay there. Can you see that that formula works nicely? Right? When x is 4, is y 40? Yes, it is. The area of a square is related to the length of the square. So we have length and we have area. The area depends on the length. So let's say the length of the side is 1. What's the area? 1. The length of the side is 2. 4. The length of the side is 3. 9. 4. 16. So here we're going up by 1s. And here we went up by 3, then up by 5, then up by 7. Is this linear? No. Despite that, can anybody see a formula for this one? This one equals this one squared. So it makes another quadratic, another parabola. And maybe you've seen that formula before. Area of a square is the side squared. We can see how the relationship and the formula go together. A water tank on a farm near swift current, that's important, we need to know where this water tank is, holds 6,000 liters. Graph A represents the tank being filled at a constant rate. Graph B represents the tank being emptied at a constant rate. Identify the independent and dependent variables and determine the rate of change of each relation. So our independent is on our x-axis, that is time. Our dependent is on our y-axis. In this case, it's volume. Determine the rate of change of each relation, then describe what it represents. So the rate of change is another word for the slope. The slope formula is rise over run. What you can do is you can take any 2 points on your line and figure out what's the rise and what's the run. So if I go from this point to this point, I'm going to go up this amount and over this amount. My rise goes from 3,000 to 4,000 would be 1,000. My run goes from 60 to 80 would be 20. So for graph A, the slope would be 1,000 over 20, which reduces to 50. We're not going to describe what it means yet. For graph B, we take 2 points, go from this one to this one. What's happening on my rise this time? It's going down. So I'm going from 4,000 to 2,000. What's that change? Negative 2,000. What's my run? From 20 to 40, it's still increasing. My run is still increasing, so that would be positive. And we find that slopes of lines that go down like this from left to right are negative. Now, a slope is rise over run. So if we wanted to include the units, the rise are your y units, your run are your x units. So here in this picture, if we wanted to add units, our y is volume, our x is minutes, oh, that one should be in blue. Very nice. And this one in green. So when describing the meaning in graph A, the water is being filled at a rate of 50 liters per minute. In graph B, the water is being emptied at a rate of 100 liters per minute. In graph B, why didn't I put the negative sign in when I wrote my sentence? Yeah, the word emptied means that it's going down, right? So our description helps show it. Our mathematics uses positive and negative numbers to show increase and decrease. Our language, we can show that using words of where things increase and decrease.